Welcome back, everyone. So this is the exercise with which I'd like to end today's class. I'm going to guess that you're probably going to need some extra time with it, so we'll consider this exercise to be our recitation activity for Thursday as well. So I'll write up a quick summary of the answers to this exercise. But in this video, and maybe I'll need to split it into two pieces actually, what I'll do is I'll talk through how I would solve this problem in detail. Okay, so we have this wave function, which I've written down here, and I told you that this is supposedly a symmetric tent wave function. Our first task is to try and sketch this thing. Now, everybody has their favorite strategies for curve sketching, but we can, I'll tell you about some of mine. Let's start by drawing our axes. And we'll start with just the wave function psi of x. Assuming n is real, this wave function happens to be real, although as we'll see later on, we do need to remember that in general, the wave function is complex. Okay. Now clearly from the definition, the points a over 2 and minus a over 2 are important. That's a little bit further. Let's skip this. Like that, minus a over 2, okay. Well, we know from the second half here that, whoops, if the absolute value of x is larger than a over 2, so for x greater than a over 2 or less than minus a over 2, the wave function is identically 0. So we've got those points already. Sometimes it helps to sketch graphs by just plugging in a few values. So 0 is usually an easy value to put in. 0 puts us up here, right? So absolute value of 0 is 0. And so we see that at x equals 0, the wave function has a value of n a over 2. Put a dot there. Let's see what else we might piece out of this definition. Now for positive x, right, we know that the absolute value of x is just x. So out here, the wave function is just n times a over 2 minus x. So that should be a linear function. If it's minus x, it's got a downward slope. We might notice from here that if x is equal to a over 2, right, then the term in parentheses here vanishes, and the wave function is 0. So we might be able to draw in that point, and we already know that the wave function is linear, right? We argued out here and has a negative slope. So we can probably draw this in like so. Similarly over here, well, for x less than 0, I told you it was a symmetric tent wave function. You can probably already guess what it looks like. But for negative x, right, the absolute value of minus x is x. So out here, it's the parentheses term is a over 2 minus x, or plus x. So we have an upward sloping line. Same logic as before, gives you the rest like that. And that should be a straight line. We can now try to draw the probability density. So if I do that, so I'm just squaring my wave function under the assumption that my wave function is real here, that my normalization constant is real. But now if I just square this, right? And we have x, we have a over 2 here, and we have minus a over 2 there. If we square this gives us n squared a squared over 4 at x equals 0. If I square a function that's linear, I'm going to get something that's quadratic, right? So just thinking about that, I'm going to get a segment here that's sort of part of a parabola, something like that. And on the other side, again, part of a parabola. That's not super even, but I think you get the idea. So part B asks us to normalize this wave function, that is, to determine the value of n in terms of a that makes this wave function properly normalized. At this point, I want to point out one useful fact. Notice that our wave function is even. That means we're going to be able to use symmetry to save us a bunch of work as we go forward. Okay, so our normalization condition says that the integral of our probability density over all of space is equal to 1 dx. Oops. Now, we can simplify this a little bit because, right, we know that the wave function is 0 if x is bigger than a over 2 or less than minus a over 2. So I can change the limits of integration to go from minus a over 2 to plus a over 2. But this is where we can take advantage of the evenness of the probability density. And that's actually really nice because the form of the function is going to be different for positive x and negative x. So it's nice to only have to deal with one side here. So let me annotate this. So let's call this to psi vanishing outside for x greater than a over 2. And so now we'll use evenness to say that this is twice the integral from 0 to a over 2 of psi of x modulus squared dx. This is even. Okay. Alright, and so now this means that I can just take what the function looks like for positive x. So that gives me the following. So I get 2, 0, a over 2. I now need to take the modulus square of this. Technically, if we let n possibly be complex, I'll just write this out as modulus of n squared. And then I want to square this piece. That's definitely real a over 2. We're at positive x, so absolute value of x is just x. So I have that quantity squared dx. So at this point, I just need to evaluate this integral, set it equal to 1, and then solve for n. That's what I'm going to do. Okay, so let's carry on here. Let me start by just multiplying this out here. I can pull out the the modulus squared of n, since that's a constant. And so we have integral 0 to a over 2 of, now just multiply this out, FOIL it, let's see, I have a squared over 4, we have two cross terms, so we have minus 2 times a over 2 times x, and then my last term is plus x squared, and all of this is being integrated with respect to x. Okay, so let's just integrate this. This is a polynomial. Hopefully you remember well from Calc 1 and 2 how to integrate polynomial functions. Well, this first term here is just constants. So if I do this, let's just have big parentheses here. The first term integrates to a squared over 4 times x. This term over here is linear in x, so the x integrates to 1/2 x squared, so we have minus 2 times a over 2 times 1/2 x squared. And then anti-differentiating this last term here, we have x cubed over 3. Okay. And we have to remember that this is a definite integral, right? So if I put the evaluation bar and our limits of integration were a over 2 and 0, we can simplify this a wee bit. So we have a 2 modulus squared of n, we have a squared over 4x, we have, let's see, we have those two factors of 2 cancel, so we have minus 1/2 a x squared plus x cubed over 3. There's an x in each one of these terms, so evaluating that at 0 is going to kill everything off. But at the upper end point, we have then 2 modulus n squared. And let's see, so we have, putting in a over 2 here, we have a cubed over 8. We have minus 1/2 a squared, a cubed over 4. Okay. Yes. And then we have, so 1/3 a cubed over 8. Okay, so this turns into minus a cubed over 8, which cancels out this term. And so the only thing that survives is this last term here. And so plugging all of that in, I have a 2 canceling knocking out a 2 down here, which gives me 3 times 4. So I end up with 1/12 modulus square root of n times a cubed. And that all has to equal 1. At this point, we can go and solve for n. And we'll assume that n is real here. And then what this leads us to then, so I'll just write the result down. We have n squared. I'll drop the complex modulus bars since we're assuming n is real now. And that gives me 12 over a cubed. And so that gives me n equals the square root of 12 over a cubed, and maybe we could simplify this a little bit. Sure, why not? If I pull a 4 out of the numerator, square root of 4 is 2, so that gives me a 2 root 3 over a to the 3 halves. The next part asks us to calculate the probability of finding our particle between x equals 0 and x equals a over 4. So now we just have to integrate the probability density again. So that probability is now going to be equal to the integral from 0 to a over 4 of our probability density with respect to x. Now we already worked out the indefinite integration here from doing the normalization, so we can actually just reuse a bunch of our work. Let me just write out the step here. So pulling out the normalization constant, we have 0 to a over 4. We have a over 2 minus x. We're on the side, we're at positive x here, so I can drop the absolute value bars, dx. And like I said, we already did the hard work of integrating this, so we'll just use that result. So that leaves us with n squared, and I'll just copy the result down. We have a squared over 4x minus a x squared over 2 plus x cubed over 3, evaluated between a over 4 and 0. Let's plug and chug and also use the fact that we found the normalization constant already. So the n squared gives me a factor of 12 over a cubed. Right? And so plugging in a over 4 in this term, a squared over 4 times a over 4, okay? Minus a over 2 times x squared, which is a squared over 16, plus 1/3. A over 4 cubed is a cubed over 64. And then, once again, evaluating it at the bottom endpoint at 0 gives us nothing. We now just have to simplify this thing. Notice that there's an a cubed in all three of these terms. That cancels the a cubed in the denominator here. That's a good thing, right? Because this probability ought to be unitless, and we know that from how the graph is set up that a has got to have units of length. So canceling my factors of a, I get 12 here. So we have 1/16, let's see, minus 1/32, and a plus 1. 3 times 64 is 196. Okay, we'll get a common denominator here. So that, let's see what we can, let's pull out some factors of 16. So that gives me a 12 over 16 to 1 minus a half, and then plus 1/12. 16 times 4 equals 64, so pulling out a 16 gives me 3 times 4. Okay. And so we just need to simplify this now. Let's place it up to, I'll just roll over to the top. So rolling back up here, we get the probability. That gives me 3/4. So 1 minus a half is a half, plus 1/12. So a half is 6/12, so we have 3/4. 6/12 plus 1/12 gives me 7/12. And so canceling factors of 3 here, I end up with a probability is equal to 7. 4 times 4, 7/16. So let's think about this, right? So the probability is a little bit less than a half that the particle is going to be between 0 and a/4. So remember from the parabolic shape of my probability density, right? So that, right, it's a parabola, and it looks something like this, right? I think you get the idea. Right? Most of the probability is sort of inside, a/4 is inside this region here. There's not a whole lot out in the tail here between a/4 and a/2. We know it should better be less than a half because we've got the whole negative side to think about. So, but looking at this and the result, it seems to at least be plausible. The next part asks us to find the expectation value of x. Now here is where we'll take the clever way and think carefully about the symmetry. So now remember that by definition, the expectation value of x is going to be the integral, and once again, because the wave function is 0 outside plus or minus a/2, I'll just put that in the limits. That's the integral of x times my probability density psi modulus squared dx. But here is where we can be clever. Right? Notice that we settle for our wave function and hence our probability density are even. Well, x is odd, as we said. Therefore, this entire integrand here, x times our probability density, that itself is an odd function. And if we take the integral of an odd function over a symmetric interval, which is exactly what we're doing, well, that just integrates to 0. 0, because the integrand is odd. So never be shy about using symmetry to save yourself a bunch of work like we just did. Finally, we're asked to find the uncertainty in x, delta x. Here we can make use of the theorem, right, that the variance or the uncertainty in x squared is equal to the expectation value of x squared minus the expectation value of x quantity squared. We just argued that this vanishes, so it suffices to calculate the expectation value of x squared. I think you might be catching on to how this game gets played. So once again, we have this. We have an x squared here now. Our probability density dx. Now, notice that this time, this is even, that's even. The entire integrand here is even. So, this saves us some work again. We can just change the limits to 0 to a over 2 with a factor of 2. So that gives me 2 times 0 to a over 2 x squared. And now I can just put in n squared a over 2 minus x 1 to d squared dx. We've done all the physics. At this point, it's a matter of chugging through the calculus. So let's go ahead and do that. Okay, so I'll pull out constants. So we have a 2, we have an n squared out here, 0 to a over 2. We have an x squared. I'm going to use what we had before. I have an a squared over 4 minus 2 times a over 2 times x, minus, that gives me a minus ax plus x squared dx. Multiply in the x squared here. So that gives me a over a squared over 4 x squared minus a x times x squared is x cubed plus x to the 4th dx. It's another polynomial, so let's evaluate it. Oops. Equal 2n squared. So we get a squared. I bring down a 3. 4 times 3 is 12 x cubed minus a over 4 x to the 4th plus 1/5 x to the 5th power. Whoops, that doesn't look very good. And now evaluated from a over 2 to 0. At this point, right, again, evaluating at the lower endpoint gives us nothing since we have x's in all of the terms here. So rolling over, we have, so carrying on, we have 2n squared, we have a cubed over 12 times 2 cubed is 8 is, so 12 times 8 is 96. A cubed over 96 minus a over 4 times a to the, oops, I have an a squared here, that should be a to the 5th. So I have a times a to the 4th, that gives me an a to the 5th in total, 5 total. 2 to the 4th power is 16. 2 cubed is 8, 2 to the 4th is 16, plus 1/5. A to the 5th times over 32. So at this point, let's just simplify the heck out of this. So we already know what n squared is. That's 12 over a cubed. And then we have a 5th everywhere. So that comes out. And so we have 1 over 96 minus 16 times 4 is 64. 1 over 64 plus 1 over 160. Okay. Okay, so at this point I can simplify a little bit here. I'll pull out factors of 4. So that gives me, so I'll simplify I have a 24 here. I have an a squared. I'll pull out a factor of 4. So that gives me 1 over 24 minus 1 over 16 plus 1 over 40, and let's try and simplify this further. I can pull out another factor of 2 here, so that gives me 20, so I have a 24 and 4 gives me a 6. So that lets me simplify this piece here. I have 6a squared, and then there's a common factor of 8 in all these denominators, so I'll pull that out. And that gives me 1/3 minus 1/2 plus 1/5. All right, so we're almost done. So now this simplifies to 3/4 a squared. And let's get a common denominator here. So that's 30. So that's 10. 30 minus 15. 30 plus 6 over 30, and so we get 10 plus 15, 10 minus 15 is minus 5, plus 6 is minus 1, plus 6 is 1. So this is equal to 3/4 a squared times 1 over 30, or a squared over 10. So we've shown here that the expectation value of x squared, if I simplify this, I have a squared over 40. So we've shown that the expectation value of x squared is a squared over 40. Now we can just use our theorem. So the uncertainty in x is square root of a squared over 40, because it's just going to be the square root of the expectation value of x squared. So now the numerator simplifies to a. We have a 4 times 10 downstairs, so we have 2 root 10. And so now, right, if you go and plug that into a calculator, what you'll find is that this is approximately equal to 0.158 a. And thinking about that seems kind of plausible, right? It should be considerably less than a over 2, from looking at the shape of that probability density function. So that brings us to the end of today's work. So when we come back for Friday's class, we'll spend some more time looking at the Schrodinger equation and starting to think about the physical meaning of solutions to it. See you then.